the public. Jiri Lipovsky will tell us about resonant asymptotics and all that.
Okay, thank you for the introduction. I will talk about resonance asymptotics on quantum graphs and hedgehog manifolds. And the work is based on joint papers with Professor Davies from London and Professor Exner from Řešení in Prague. First, I will introduce quantum graphs and describe the model. Then I will talk about resolvent and scattering resonances, the two definitions of resonances. Then I will go to the main part, which is the asymptotics of resonances, first for non-magnetic graphs, then for magnetic graphs. And if I have time, I will say something about hedgehog manifolds. So, what are quantum graphs? We are interested in some network structure and a quantum particle on this structure. So describing properties of quantum particles on these network structures. It was first used in the 1930s and then later in the 1950s, in 1930s by Pauling and 1950s by Riedenberg and Scher, and they described some properties of aromatic molecules with this model. It has been developed mainly in the last 30 years, and it describes various mesoscopic systems as quantum wires, nanotubes, photonic crystals, and so on. And it's not only a theoretical model, it can be really measured, and there is at Polish Academy of Sciences the group of Leszek-Czirko who measures properties of microwave graphs, and these microwave graphs correspond to quantum graphs. So the properties of quantum graphs which can be computed correspond to these measurements on microwaves.
So people are talking about quantum computer. This is classical computer which really mimics quantum physics.
Yes. There, as you said, it can be used for...
Which is quantum because it's built by transistors.
Yes, but what really matters are classical waves.
Yeah.
It can be used for designing elementary gates in quantum computing, or since it's from a mathematical point of view quite a simple model, it's the set of ordinary differential equations. So it can be used as a toy model, for example, for describing quantum chaos. And there are other models which are similar to quantum graphs, for example, leaky quantum graphs, and also behavior of the Dirac operator on graphs can be studied. So now I describe the model. As I said, it's a set of ordinary differential equations. So we have a graph which consists of the set of vertices V, set of internal edges, and set of external edges. These external edges are half-lines. The Hilbert space of this problem consists of square integral functions on the internal edges and external edges. And the states in this Hilbert space are described by these columns. So we equip this graph with a quantum Hamiltonian, which acts as minus second derivative plus potential, which is bounded and which is supported only on the internal edges of the graph.
I apologize for being completely uneducated, but there are symbols which perhaps you could make more familiar to us. For example, what means capital I with the subscript script L?
Yeah, sorry.
Down the product.
Yeah, here.
I know it's obvious, but just for me.
this corresponds to the internal edges. So this
IL is what?
This is IL is the set of vertices, which are not which are internal vertices, and here
And they are for some reason labeled with 2 indices.
this is for each edge. So each edge is labeled by
So it's a number of
by
vertices or edges?
this orthogonal sum is over the edges, and the edge is described by 2 numbers.
So IL is not the number of vertices but edges. This way or another.
J and N are numbers of vertices.
So it's a 2-dimensional set. I mean,
Each edge is labeled by 2 vertices.
but J and N are labeled for vertices.
Vertices.
Edge is between 2 vertices and the numbers refer to vertices.
Yes, and
So J and N, J is in the J labels vertices.
yes.
So the IL is not the set of the vertices but edges. And it was said just before that it is a set of vertices. No, it said vertices. And that's why it was confused.
And here is the sum over all half-lines. Here. So we have
Again, I don't understand. So I now know that J labels
J
vertices.
levels vertices.
J and, or N or
and
whatever,
N.
right? And then there is some index capital I with the labels JN. L square of 0 of L JN. What? This is the distance between what?
Integrable function
On what?
Integrable function on the half-lines.
Yes.
Yeah?
On the half? No, I'm talking about
Here on the interval.
This is
I'm
on the
talking-
interval.
These are functions
on the distance between J and M.
on the edges. Interval.
Yeah,
On the
okay.
edges, on the interval
Yes.
from 0 to L.
So what are the external edges? They go to infinity.
External edges are
This
half-lines.
Okay.
It's like that you have
It's nice to know what this meant.
a graph, which is the internal part of the graph, and you touch some half-lines. In this graph. And the Hilbert space consists of square integrable functions on the internal edges and the half-lines. So it must be square integrable over all the graph.
And FJN?
FJN is
F
the
in the lower.
function, the component of the wave function on the JN's edge, and FJ infinity
No, that's obvious. But
is
epsilon JN?
epsilon JN is the JN's edge,
What?
which is the edge which is between the vertices J and N.
But what is epsilon A? There is FJN is a wave function sitting on the edge.
This is the
And
wave function
epsilon JN is what?
This is script E.
What?
This
It's
is
a script E. Well, apologies for
yeah.
misuse of the language, but I mean, whatever
But
it is.
this means the edge between J's and N's vertex. So, for example, I have
So
the
it's
vertex
different from
1.
LJN. What's the difference, if this is the edge, what's the difference between script JN
I have
and
here,
IJN?
I have here edge E12, which is the edge E12, and the length of this edge is L1. and this edge corresponds
Yeah,
to the
but
interval
In the
from 0
upper
to
line,
L1.
this distance was called IJN.
Yes, because that was the length, and this is the space.
No, this is that J
No,
and
the inside of L square.
well, here this is the edge, and this is the index subset or index set corresponding to the vertices.
LJN is the length of the edge.
Yes.
LJN is
Yes.
here the length of
And
the edge.
IJN is just
The Hilbert space could have been denoted also, instead of 0 IJN, one could put there EJN as the space on which the wave function is defined.
Yes.
yeah, that's what my question is.
Yes.
So there is basically no difference
There's
between
no difference.
IJN and epsilon.
No, there is some difference, but not.
For primitive individuals, it's the same.
Yes.
So
I
the
have
rate
maybe a
is-
stupid question. Is there any reason why you have the sum, not the product of the Hilbert spaces of the subsystems? Because typically when we think about Hilbert space, which is composed from about the system which is composed from some on some subsystems, then we have the product of Hilbert spaces, not the sum, because sum is not a Hilbert space.
But these are not subsystems, they are connected.
This is my question. If we can treat each line as a subsystem,
No,
which is described by
that would not be
So,
correct.
If that's one
Because these are
system.
not independent subsystems. They are connected.
There are many subsystems which are not independent. Usually subsystems are not independent.
Because they are coupled.
sure.
Yeah.
So why is
I
it
will
not a
come
product?
to this later.
But still, it should be a product of Hilbert
No,
space.
if you have a wave going through a potential step, you don't say it's a product of the wave inside the step plus the times the waves which go outside of the step.
It's like a
This is
single
not
particle
a
living
product.
on the graph, not a field.
Yes.
So yeah, the Hilbert space has several components on these edges, and
So this is not a Hilbert space, but the configurational space
No, it's a Hilbert space.
is the sum of
No, it's
this.
a Hilbert
It
space.
is.
Yes, but the Hilbert space is on the yes, the graph is the the space of configuration. It's not a, it's the, just a, like a line or something. He has functions of this on this graph, not the.
yeah, functions. It's a
So it
space
should
of-
be L squared
of
on
functions.
the sum of these lines, not sum of L squares. Because L square is a.
That is the question which that there is probably some valid difference.
I think the problem is much simpler than this notation which is.
But that's the point.
So, but this problem is very simple. You have a wave function on this space.
Yes, so each the Hilbert space is a L squared on the sum, not the sum of the L squares.
It can be a sum of the L squares.
But typically we say that it is L squared on the
yeah.
on the
Yes.
graph, not the sum of L squares, because it is misleading, I think.
But I think
And that's
there's
not
a-
identical, of course, because if you have a function of a very complex landscape, which is square integrable, it need not be square integrable at various
On each piece of it.
Yes.
you know.
This is the point.
So there is some confusion in your
Well, it says that it's a collection of wave functions which are square integrable on each
Yes,
step.
it should be, otherwise it would be square integral of the whole graph.
That is not true.
If you assume that this is a finite graph, then it's the same.
Because I can
If you
imagine the
admit
wave
infinite
function
number-
which is square integral of the
Przecież
whole
mówię,
graph.
to jest L
But
squared.
for some people, which has because it gets crazy in some point and in the other direction and it cancels, right?
Absolutely. Yes.
Well, absolutely.
Yes.
The modulus squared must be bounded on each. Why?
Why?
Because This is L squared on each.
Oh,
From this definition, it
definition.
follows
Yeah.
that if you would define the function on the whole graph,
Graph.
which is square integrable, that it need not be composed of the functions which are piecewise belonging to the square integrable set.
I think it must be.
No, but that is the simple example is you take a polynomial, which of 127 degree on a distance 0, 1, and which is constructed such that between 0 and 1/2 it behaves like crazy from
Then it's not square integrable.
it is on the whole thing, yes, because I can subtract the
No,
negative.
But perhaps we can continue discussion after the seminar.
Probably irrelevant for
It's probably irrelevant because for the Turskis and mine
Yeah.
objections to apply, there would have to be singularities at vertices. And probably that
for
is
example,
excluded.
That's the point. Okay,
So we have this Hamiltonian, which corresponds to the Hamiltonian of a quantum particle. So it's
and
really-
x is a distance on the edge.
no,
Yes.
this is the whole X. You mean-
X-
Yeah, but only
X
on the edges.
is-
It does not exist outside of the edges. This particle.
Only on the
Yeah,
rest of
only on the edges.
Yes.
Only on the edges. And here we take the set of units.
And on each of these, on each of the links, there is the same potential. That is just V.
There should be J or JN. Yeah, there should be JN. I'm sorry. There should be JN.
Also,
Oh,
also
there-
X is symbolic
yeah.
here.
Well, V here can mean that it's correction of the potentials that so there is different potential on each edge, but in many applications I will take the potential to be 0. And here we take that h bar is equal to 1, n is equal to 1/2 to obtain here minus second derivative to have things simple. And the Hamiltonian must have a domain which consists of the function in solar space W22 on the whole graph, which is orthogonal sum of the solar spaces W22 on each edge. And these functions must satisfy the coupling conditions at the vertices.
So that's really fun.
And
Very stupid question. Before we were considering the space L2 for the functions. Symbolic space is that I have the second derivative of the wave function is normalized, am I right? Or no? Is W22 consist in L2 or not?
Is this fun is something W22 gamma different from this
W22 is the
from this
space,
H?
space
defined
of the
before?
functions where the function, its derivative and second derivative are L2 in
So it's wider than L2.
It's inna funkcja.
Sorry, it's narrower than L2.
Yeah.
So this W22 gamma is a subset of this kind of space.
Yes.
So this is the functions out of the Hilbert space which satisfy some funny conditions on each vertex, right?
Because we must add to the Hamiltonian.
Yeah,
Absolutely.
we have here second derivative. So that's why we have the super space to be able to define the second
The
derivative.
space must be in the domain of the Hamiltonian.
Yes, otherwise.
And these coupling conditions bind the vector of the function values, the limits of the function values in each vertex from each edge, and the vector of outgoing derivatives in each vertex from each edge which emanates from this vertex. And it's given by this equation where A is a square D times D matrix and B is also square D times D matrix where D is the degree of this vertex, number of its neighbors. So we have this equation this
So
coupling condition.
is this the same as saying that there are continuity equations at each?
No, not really.
This must be
These
some kind of
compare law.
Kirchhoff's law.
Oh, yeah.
yeah, it's
So what
sometimes,
zero
but
comes
not
out
only continuity condition. One of the possibilities is the so-called standard condition, which is Kirchhoff or Kirchhoff condition. But it's only one of the possibilities.
Okay, so it's more general.
And to have a self-joint operator, the matrices A and B must satisfy that A, B, Geiger or Hermitially conjugated is A Hermitially conjugated B, and the rank of this rectangular matrix which joins
Excuse me,
A and B.
coefficients A nu are always different from zero? Or they can be equal?
This is a matrix and it can have 0 entries.
So it's not the product for each nu.
It's V. It's V and
Well, whatever.
and it is vertex.
And
This
it's
is
for
the vertex.
so I'm asking
There's no
for,
summation over it.
yeah, so it's for each of the vertices,
Yeah.
however we label
Yeah.
them, right?
Yeah, but
Therefore,
this is
can
not-
I consider the situation where a set of four
To
A,
yes,
B
to
is
yes.
equal to zero?
Yes.
Then the particles do not propagate because the
Yes.
current on each
Yes.
vertex is zero. So the particle, because a psi prime is a
So
current,
this is not a very interesting case.
so it's not
Yeah.
limited.
Yeah, you can have, for example, so-called Neumann conditions where the derivative is equal to 0.
Mhm.
So it means that A is equal to 0 and you have that psi prime is equal to 0. And it's separated. Or Dirichlet conditions, for
Yes.
example. Yeah.
That's a situation where some B's are zero.
And if you multiply this equation from the left by a regular square matrix C, then you obtain exactly the same condition. It corresponds to the same condition, but with different matrices. So this equation is not unique, and there is a unique way how to describe this condition, and it's by this equation, where U is a unitary D times D matrix, I is a unit matrix, and you have here complex unit I, and again U plus I times psi prime. So you have here this equation which I will use later. So in each vertex you have this condition. Here I have particular examples of coupling conditions. One of the possibilities are so-called delta conditions. It corresponds to the delta interaction. Here function values are continuous in each vertex, and the sum of the outgoing derivative
Goes out,
Everywhere it goes, if you open the door, it goes everywhere, there's no graph. There's no connection between these.
okay, so I modify my model. I make my
No, but let's give the
So, but
speakers
then
a
what-
chance to tell about asymptotics, because this is the main subject of this lecture.
So, we are interested in the asymptotics of the resonances, we are interested in the number of resonant resonances, which are enclosed in the circle of radius r in the k-plane, so in the square root of energy, for r big enough, for r going to infinity. If we have, for example, a compact quantum graph, then you have eigenvalues, and these eigenvalues follow the while law. So the number of these eigenvalues is given by the while law, and it's given that by 2v, where v is the sum of the internal edge of the length of the internal edges of the graph over pi times r plus the residual term, this is O of 1. So there is an extra term of 2 because you count every eigenvalue twice, because k squared is equal to minus k, the whole thing squared. So you expect this behavior.
So the number of resonances is always infinite? The total number?
The total number is
Always for every graph?
there exists graph where it's, for example, 0 resonances or finite number of resonances.
So,
But you would expect infinite number. Yeah? Because
infinite number for a simple graph?
for a simple graph, because for example, if you have an interval, no half line,
Yes.
then you obtain eigenvalues like this,
Yeah, real.
n pi, for example, or something like that.
And then when you open this, this becomes an infinite.
And if you
Then you
have
have
this
resonance.
with some interaction, then these resonances, these eigenvalues go to the complex plane. If you have here, for example, first Dirichlet coupling, and then you slightly change the coupling and open the interval, then these resonances go to the complex plane.
So this is just by saying that you have a box, potential box, and then you have infinite number of states, and by changing this to an open box, you get a shift to, okay,
Yeah.
Because they are leaking.
yeah, they are leaking. But yeah,
I dlatego są.
But what is interesting, there exists graphs for which this number here is smaller than expected. One example is here. So you have standard coupling or Kirchhoff coupling, and you have here this vertex. For standard coupling, you have the function value is continuous and the derivative is continuous. So there is no interaction at all at this vertex. So that means that I can replace this by one big half line. So the effective size of this graph is smaller. So effectively, you have to count the length of these edges only and not this edge. So this constant is smaller than expected. And it was studied for standard coupling by Davis and Pushnitsky, and they found a nice geometrical condition when the graph is vile and when the graph is non-vile.
what does it mean?
It means that the graph is vile if there is this counting function, and non-vile if this constant is smaller.
Why the name of vile is invoked here? It was vile.
Because it flows the vile law,
Which is?
which is this for eigenvalues. Weil studied the number of eigenvalues which are.
Hermann Weyl had solved this
Yes,
problem.
I think Hermann Weil. Number of eigenvalues which are in modulus smaller than some number. And he studied it also for more dimensions, but for one dimension it's given by this expression. So the graph is non-vile, so the constant is smaller than expected. If and only if the graph with standard coupling contains a vertex which is balanced, and by balanced vertex I mean a vertex which connects the same number of internal and external edges. So for example, this graph has this vertex which connects two internal edges and two half lines. So this graph is non-vile. And we tried to generalize this result for all possible couplings for self-adjoint operators, and we found that the graph is non-vile if and only if this effective coupling matrix U tilde has eigenvalues either 1 plus k over 1 minus k or 1 minus k or 1 plus k. One of these eigenvalues corresponds to Kirchhoff condition, and one of it corresponds to its counterpart, which we call anti-Kirchhoff condition. The idea of this proof is that you write down the condition for resonances. You obtain it by complex scaling, for example. And in the condition there are exponential polynomials. So some polynomial of k times some exponential of k. And there is an old result from 1930s that zeros of these functions are located in logarithmic strips, and its counting functions behave as this, and from this flows the claim of the theorem. And what we also studied were non-viral graphs for permutation symmetric coupling. So permutation symmetric coupling is the coupling where if you interchange two edges, then you obtain the same coupling. So it's symmetric with respect to the permutation of any two edges which emanate from this vertex. And these coupling conditions can be written by this matrix U, which is A times J minus B times I, where J has all entries equal to 1, and I is a unit matrix, and A and B are complex parameters. To obtain a unitary matrix, there must be some conditions satisfied, and it is that B in modulus is 1, and B plus degree of this vertex times A in modulus is equal to also 1. And we obtain the result that two conditions must be satisfied to obtain a non-viral graph. First, you have to have balanced vertex, and second, you have to have either standard coupling or Kirchhoff coupling or so-called anti-Kirchhoff coupling, which is given by this unitary matrix. The proof is quite simple. You compute the effective coupling matrix, and then you compute its eigenvalues and compare it with these 1 plus k over 1 minus k or 1 minus k over 1 plus k, and you obtain that only for these two possibilities it is satisfied. Here I have an example which shows how why the effective size is smaller, how one can delete some internal part of the graph by extending one half line. And this consists of a loop of length 2L and two half lines attached at one point. We introduce another vertex here in the middle of the loop with standard coupling, and here we have also standard coupling. And we have function f1, function component f1 here, f2 on this part of the loop, and g1 here and g2 here. And the trick is to take symmetrization of these functions and anti-symmetrization of these functions with respect to this axis. You take symmetric functions, anti-symmetric functions, you write down the coupling conditions for the previous phase function components. So you have here at the point 0, which was this point, you have standard coupling and also standard coupling for the central vertex. And if you compute the coupling conditions for the symmetric functions and for the antisymmetric functions, you obtain that this graph corresponds to, for the space of symmetric functions for Neumann coupling at the end. Here is standard coupling at the distance L. So you have one long half line for the symmetric functions. Here you have Neumann coupling, here you have standard coupling. And for the antisymmetric functions, you obtain Dirichlet coupling, so abscissa with Dirichlet coupling of the length L, and one half line with Dirichlet coupling. And that means that instead of internal part of length to L, you can extend this half line to obtain one long half line, and you have internal part only of the length L. So you deleted an internal part of the graph, and therefore the effective size of this graph is only L, not 2L, but L.
Can this problem be solved analytically?
Yes.
So there is a solution, and all eigenfunctions can be explicitly found?
Yes. Well, in this case, there are only the eigenvalues, not the pure resonances. Or there is one resonance at k equal to 0 from the Neumann, and only the eigenvalues which corresponds to this abscissa with Dirichlet coupling at both ends. So we have eigenvalues at multiples of pi.
So these are some sine functions.
Yeah, sine functions on these. And if you want the wave functions for the circle, you have sinus with zeros at this point.
But we have an open system. The waves can go to infinity. So
And zero solution on the internal edge, on the external edges.
you assume zero on the.
Yeah, you obtain only these solutions. That is,
But that does not agree with physics. I mean, you can send a wave, with this open external lines, and what happens to this wave? It will just be scattered and go out.
yeah, but you obtain these solutions, but these solutions are not resonances. In my definition.
So what you are saying is that if I will send arbitrary wave through these two leads into this loop, and then see what comes out, there will be never a resonance.
That seems strange because it contradicts what you said before. If you just have a circle, then you have cosine or sine functions depending on boundary conditions that go around this circle. Then you open this, and it will seem that this will lead to resonances. If you couple this potential well, so to speak, with the external.
Unless the coupling is in a very funny way.
No, the coupling.
The coupling is standard.
Standard.
I have
well,
a feeling
but
what's
you
the standard.
obtain in an experiment, you have here some losses, for example, or other
Let's
things,
forget about losses.
and you obtain resonances at this pi or 2 pi or 3 pi.
No imaginary part.
No imaginary part.
But this system, if you open it, it has continuous spectrum. It has continuous spectrum, so resonances are in the continuum.
These eigenvalues are included into the continuous spectrum. The spectrum of this problem you obtain.
But isn't so that we are discussing now the fact that for some reasons the resonators cannot work? Because this closed thing doesn't look like a resonator. And then if I have a resonator and I send the waves, then by just the name of resonator, there are resonances. So I mean, I can take a fiddle and the camera tone and I can easily produce the resonance for each side, each shape of the fiddle. So something is I mean, probably everything is perfectly correct here,
Maybe it's
but we
hidden
are
in-
something missing in physics.
Maybe it's hidden in this boundary.
Yes, something is missing. We don't understand when you said standard. Probably what you understand as a standard is deeply unstandard for such a primitive individuals like me.
This is a very simple system. Yeah, you have first, let's do it in steps. First we have a loop. There are no external lines. Then we have
Discrete
a
spectrum.
very simple situation. We have a discrete spectrum. There are only cosine and sine functions inside. Then, yes, then we open this system. We allow the probability.
There is something special here. There are two leads coming to this.
So,
But why is that important?
I think it's not important, but if you solve mathematically spectrum of this problem,
yeah.
then you obtain these eigenvalues plus from 0 to infinity.
You don't tentatively
continuous
assume that
spectrum.
there are some boundary conditions on the G1 and G2
Maybe
in
there's
infinity which are
some
different.
very strange boundary conditions.
Yeah, I mean, but if there are some funny things happening at the ends of
You say that
these,
the continuous spectrum is embedded in the
Eigenvalues are
is
embedded
embedded in the
in the continuum.
continuum, and there are no shifts, there are no imaginary part of the
Oh, yeah.
spectrum.
But if you really want to construct these solutions or this problem, then you don't construct the exact standard coupling. You have something which is close to the standard coupling, but a bit different.
what do you mean by standard coupling?
Kirchhoff coupling.
So the conservation of probability
Yeah.
Is not satisfied.
is not
Ah.
A bit.
So there are some, so that's what was standard is slightly unstandard.
If you
Yeah, but this
experimentally
slight
realize
is
this
now big.
problem, then you obtain something which is a bit different than this coupling condition, which I have here mathematically, and
It's
you
slightly
obtain
bigger than.
something which is these angles become resonances, for example, and you obtain
in real life they become
in
resonant.
real life resonances.
Okay.
So how much time do I have?
Well, you
No.
So I thank you for your attention.
Well, it would be nice to have some connection with the real physical systems.
At least with hedgehogs.
Maybe you can say yes. In 2 sentences, what are hedgehogs?
A hedgehog manifolds is a Riemannian manifold with attached half-line.
Oh, okay.
So Riemannian manifold and attached half-line, like a hedgehog.